Hello and welcome, dear students. Today we are going to discuss an important topic on techniques in hydrology and hydrogeology. As you know, hydrology and hydrogeology is a multidisciplinary subject. It involves several branches of science to understand the complex surface and subsurface components of the hydrological cycle. The scientific disciplines uses instruments, techniques and technologies. These tools are vital for understanding the systems, managing resources and mitigating water related disasters. In recent decades, advanced technologies are integrated with the existing methods to enhance the accuracy and efficiency of water management. The module provides the basic concepts about the common and key techniques in hydrology and hydrogeology. First, field techniques. Field data is important to understand the hydrological cycle and the processes. Several approaches are used to collect and analyze the field data from the watersheds. They include GPS and DGPS. The location and elevation data is collected using global positioning system and differential global positioning system technologies. They provide high precision spatial data for different purposes. Standard GPS receiver connects with at least 3 satellites and determines the position of a point. The accuracy varies by 3 to 10 meter. Modern receivers and DGPS enhances the accuracy to even centimeter scale. DGPS uses fixed ground reference stations that transmits real-time correction signals to rover units. Nowadays, DGPS is used to provide accurate cross-section of rivers, monitor groundwater, map floodplains and major glacier movements. They have been successfully used in Himalayan and other catchments. Camera is a vital tool used to record pictures and videos of important features in the field. Modern cameras monitor water levels and estimate flow velocities. Recently, cameras are combined with image processing, machine learning and drones for flood forecasting and water management. Measurement of precipitation. Precipitation, either rain, snow, hail or mixed, is measured by various instruments. Common ones are the rain gauges, which may be of simple measurable cylindrical tubes, tipping buckets or weighing gauges. Government launched Mission Mousam program to transform India into a weather ready and climate smart nation. Presently, the Indian Meteorological Department has extensive network of more than 2,600 automatic weather stations and automatic rain gauges for continuous data collection. The IMD defines the long period average precipitation as the mean rainfall between 1971 to 2020. The value for the country is approximately 1160 millimeter or 45.7 inches. Snow plows and lisimeters. These instruments measure the snow accumulation and meltwater. Precipitation radars quantify the interception losses in the forest areas to model hydrological budget. Now, measurement of evapotranspiration. Evaporation from water bodies and evapotranspiration from plants and grass is measured using a pen type instrument. This is filled with measurable water volume and the drop in water level is recorded each time. For direct ET measurement, lisimeters provide a most direct and accurate measurement by weighing soil plant systems over time. Similarly, eddy covariance provides long-term data sets of ET. In addition, new sensors like scintillometers are used for different land use and geological settings. However, the instruments are expensive and need frequent maintenance. Evapotranspiration has two components: actual evapotranspiration and potential evapotranspiration. The average annual actual evapotranspiration is approximately 573 millimeter, or roughly half of the country's average precipitation. Likewise, the average annual potential evapotranspiration is approximately 1547 millimeter. Measurement of soil moisture. Soil moisture represents the amount of water stored in the soil column. A standard method to determine this water content is by oven drying soil samples at the laboratory. The weights are measured before and after drying to estimate the water content. Another method is based on estimating the dielectrical properties of the soil. It measures how the soil stores electric energy and lose it under given electric field strength. The equipments are expensive and require frequent technical calibration. Neutron probes measure the depth-wise hydrogen content in the soil profiles. However, the probes need safety regulations. Similarly, capacitance sensors, tensiometers and heat pulse probes are also used. At large scales, microwave remote sensing is used. The volumetric soil moisture can vary from 25% to 45% in different soil types of India under different rainfall conditions. Now, measurement of stream flow. Stream flow or discharge is defined as the volume of water transmitting through a given cross section of river in a given time. It is commonly expressed as liters per minute. Discharge is measured by two most widely used traditional methods. The velocity area approach estimates discharge by multiplying the cross sectional area of a river and water velocity at a given time. The data accuracy depends on the turbulent or laminar flow conditions. Second is the stage discharge relationship. The stage discharge relationship, also called rating curve, provides discharge at a stream. A gauging scale measures the water level. It is converted to discharge by an empirical fitted curve technique called Manning's equation. At a specific place where both the discharge and stage are measured, the equation is generally represented as Q is equal to 76.5 multiplied by water level raised to the 4.1. Modern automated sensors reduce the errors and enable real-time data. In India, the Central Water Commission has installed nearly 133 discharge stations and 199 stage stations. The data is used for water resource modeling and forecasting hazards. Second, application of geophysical tools. A human eye cannot see the subsurface systems and processes. For this, several geophysical techniques are employed. They work in analogy to an X-ray or USG done on a human body. Geophysics employs the laws of physics such as Ohm's law, gravity, etc. The commonly used methods are the electrical, gravity, seismic and magnetic. In the electrical methods, an electric current is applied into the ground through metal electrodes and potential differences is simultaneously measured. Resistivity is the property of rock that defines how strongly the electric current is opposed. Resistivity depends on the lithology water content and solute concentrations. One of the widely used electrical methods is the electrical resistivity tomography or ERT. ERT has been able to delineate aquifer boundaries, track contaminant plumes and monitor infiltration processes. Two configurations of electrical methods are commonly used: ERT profiling, which gives the spatial information, and ERT logging, which gives the depth-wise information. Other electrical methods include self-potential, induced polarization and electromagnetic methods. Recently, the Central Groundwater Board and National Geophysical Research Institute completed the first phase of the National Aquifer Mapping and Management Project. In this study, scientists collected the geological information using geophysical methods in selected watersheds. The first phase of the project covered more than 25 lakh square kilometer area of the country. Now, seismic method. Seismic waves are generated at the focus of the earthquakes. Through the rocks, they travel with variable velocity and are reflected and refracted at the layer boundaries. The instrument which records these waves are called seismometers. The wave properties correlate with the density and water saturation of the rocks. This enables geoscientists to identify the weathered layers, aquifer structures and saturated zones. In active seismic methods, a controlled seismic source like a hammer or explosion generates the waves, while in the passive methods, natural seismic energy or seismic noise is interpreted. The National Seismological Network consists of more than 160 operational stations across the country. The program is maintained by the National Center for Seismology. Now, ground penetrating radar. GPR is an instrument that transmits electromagnetic waves into the ground and records the reflections. The waves have high frequency of 10 to 1000 megahertz. While traveling, the waves change their properties. Dielectric constant measures the ability of rocks to store electrical energy. A difference in this property between the two rock types is recorded. However, the depth of the signal weakens within the clay and saline content. Based on the type and configuration of the antenna, modern GPR surveys can provide valuable information up to 30 meter depth. Recently, GPR has been used to identify fracture and fault zones, map water bodies and soil moisture. Now, magnetic resonance sounding. Magnetic resonance sounding is based on magnetic properties of the atoms. The proton of a hydrogen nucleus behaves like a small magnet under the Earth's magnetic field or induced magnetism. Magnetic resonance is similar to the medical MRI done on humans. It is used to estimate porosity, water content and hydraulic conductivity at depths. However, the geophysical methods have technical and topographic limitations as well. They require costly equipment and technically trained persons. Third, application of hydrochemical tools. Assessment of water quality is important for ensuring safe water for domestic, drinking and sustainable irrigation. The techniques used to measure water quality include laboratory measurement of physicochemical parameters such as pH, electrical conductivity and total dissolved solids. It also includes measuring microbes, trace metals and other contaminants. Standard laboratory reagents, protocols and safety measures are necessary for such techniques. The water quality data is analyzed and interpreted using statistical methods, and computer softwares. In India, sophisticated laboratories have been installed in research institutions and universities for these purposes. Several isotopes of elements such as oxygen, hydrogen, carbon, etc. are widely analyzed in water samples for investigating hydrological processes. Stable isotopes such as H2 and O18 distinguish the contribution of rainfall, snow melt and groundwater. Other applications include identify mixing processes, paleoclimate and hydrological connectivity. The radioactive isotopes like tritium, carbon-14 and krypton-81 determine the age of water and measure recharge rates. Isotope studies in the Himalayan catchments have shown that meltwater is sometimes 30 to 40% of the total river flow and 44 to 68% of the groundwater. Fourth, groundwater monitoring techniques. Groundwater is the water that percolates through the soil and shallow layers to the aquifers. The water flows under natural conditions like a spring. It is also pumped by humans for several purposes. The techniques used for its study include monitoring groundwater levels or depth of water table is a fundamental field activity. The instrument is dropped in a well and the depth of the water is recorded. This is done manually or through electrical sounders. Automated loggers continuously monitor fluctuations that occur due to pumping, tides, precipitation and evapotranspiration. The data is useful to understand aquifer dynamics. Pumping test. In this technique, water is withdrawn at measurable rate from one well. The drop of water levels, also termed as drawdown, is recorded in the surrounding wells at known times. The time drawdown data, that is water level versus time, is analyzed using mathematical equations. The test is done for any duration ranging from few hours to several days. The method estimates transmissivity, hydraulic conductivity and leakage. Now, slug test. It is another quicker, less intrusive and more evolved method. In this, a slug of water is either added or removed from a well at once. This disturbs the water level in a well that is monitored using equipments to estimate hydraulic conductivity at small scale. Tracer technique. In this, a conservative substance is introduced in the hydrological systems. Tracer can be a natural, chemical, isotope, artificial dye or even heat. The test investigates flow pathways, recharge processes, solute transport and aquifer connectivity. In karst aquifers, the tracer technique determines age, recharge timing and mixing processes. The technique has been used in several karst aquifers of India. Packer test. It is also known as Luygen's test. In this, an inflatable packer is dropped into a bore well that isolates a section of it. Water is injected into the packer layer under controlled pressure. Water moves into the surrounding sides through pores. The drop of water in fractured aquifers is measured for water management, tunneling and dam engineering. Now, speleology. The scientific study of caves and karst aquifers is termed as speleology. Techniques such as mapping caves morphology, laser scanning, dye tracing and geophysics are widely used. Modern methods include isotopic dating and geochemistry of speleothems to reconstruct paleoclimate. Now, let us discuss remote sensing applications. Remote sensing is widely used in hydrology from small to global scales. Optical sensors, for example Landsat and Sentinel-2 and synthetic aperture radar map water bodies, flooding and morphology. Radar altimetry estimates water levels in remote water bodies. In the ungauged watersheds, it is used to construct flow data for modeling. Microwave radiation is a band of the electromagnetic spectrum between infrared and radio wave with wavelengths of 1 millimeter to 1 meter. The signal is captured by satellites such as soil moisture and ocean salinity. The analysis provides frequent data on soil moisture at global scales. Similarly, gravity recovery and climate experiment satellites detect changes in Earth's gravity field. The data provides large scale groundwater storage variations. GRACE observations over northwestern India like Punjab and Haryana show that groundwater levels is decreasing by 4 centimeter per year. The field information and satellite data is integrated in geographical information system for modeling the hydrological parameters and processes. It is used to delineate watersheds, flow modeling and basin characterization. GIS helps to map groundwater potential zones, estimate recharge and assess risk to hazards and pollution. Now, sixth is the laboratory techniques. The laboratory techniques are required to measure some important properties. Samples are collected and analyzed in the laboratory under controlled and standard conditions. However, the laboratory values may differ from actual field conditions due to scale and sample disturbance. Soil and sediments are analyzed for grain size composition using dry and wet sieving methods. Permeability tests are conducted to determine porosity, specific yield, pore water pressure, hydraulic head and saturation conditions in soil and rocks. It helps hydrologists to quantify permeability, conduct experiments on Darcy's law, study liquefaction, etc. Atterberg limits test is conducted on the fine grained soils like clay and silt to define the critical water content. The test classifies soils and predicts engineering properties. For measuring water quality, the soil and water samples are analyzed in the laboratory. The samples are treated with chemicals, reagents and titration techniques. It determines the load or concentration of different organic, inorganic and isotope constituents present in the water. For precise values, sophisticated instruments are used. Ion chromatography, inductively coupled plasma mass spectrometer and spectrophotometry are installed in major institutions of the country. However, the cost of the analysis is too high. The methods are used to determine the water quality for drinking, industrial and other purposes and estimate recharge, contamination, water rock interaction and evaporation. Now, let us discuss the modeling approaches. Modeling is a crucial tool to understand the hydrological cycle on the surface and underground. Various model techniques are used to know how rainfall turns into runoff, predict floods and manage water problems. Other applications include measure the movement of water and sediments in rivers and lakes, assess groundwater flow and contamination, etc. Models are used to see how the water resources behave under variable climate and human impacts. Commonly used models include soil and water assessment tool and MODFlow. Eighth, water management strategies. Water problems such as water scarcity, floods and pollution are managed using various methods. In preventive approaches, focus is to stop the future problems, while in the restorative strategies, the existing problems are managed or reduced such as wetland restoration. The managed aquifer recharge methods enhance groundwater levels in depleted aquifers. Similarly, tracer and solute transport models help to know the source and fate of pollutants in the water. Now, let us discuss the cryosphere monitoring tools. Cryosphere is the part of the earth that is covered under ice, glaciers and permafrost. The Himalayan cryosphere is also called as the third pole. The hydrology in these unique systems is very complex. For understanding this, a combination of field observations, remote sensing, geophysics and modeling is used. Some commonly used field methods include snow pits, fern coring and ground penetrating radar. They provide high resolution data on snow layering, mass balance and ice thickness. However, there are logistic challenges to conduct the experiments. Satellite remote sensing is beneficial in cryosphere research. It can cover those areas where humans cannot reach. Landsat and Sentinel-2 satellites provide data on glacier extent and albedo. Similarly, synthetic aperture radar captures ice velocity and surface roughness. Satellite altimetry precisely measures the elevation changes and glaciers mass loss. The snow water equivalent is measured using infrared and microwave sensors. Numerical models simulate cryospheric processes and project future responses under climate change and human impacts. Similarly, isotope data can quantify meltwater contribution, provide age and reconstruct paleoclimate. Now, what are the emerging techniques and tools? The subject is evolving and so are the techniques and methods of its study. Some of the emerging techniques are drones. Drones are becoming an essential tool of the scientists. They capture high resolution spatial data rapidly. The vehicles are equipped with latest cameras and sensors to detect the different bands of the electromagnetic spectrum. It is used in mapping landforms, soil moisture, vegetation stress, snow cover and water dynamics. Thermal sensors can detect seepage zones and groundwater surface water interactions. In cryosphere, LIDAR and photogrammetry in drone cameras provides centimeter scale glacier morphology, meltwater and snowpack evolution. They are used to detect erosion, sediment transport and geomorphic changes. There are challenges to use them mainly due to technical limitations. Another method is environmental DNA or eDNA. eDNA has been recently used to trace water movement and ecosystem responses. In these methods, the genetic material left by organisms is collected and analyzed. Fiber optic distributed temperature sensing is another emerging technique to detect high resolution temperature changes in reverse and recharge zones. Machine learning and artificial intelligence are also used in flood forecasting, groundwater prediction and quality modeling. However, the techniques are to be used with care. This was all about today's lecture. Hope you have enjoyed it well. Thank you.